Okay, so let's continue our discussion about systems and transfer function. What we focus on in this course is systems that take only one input and one output. Take one input and give one output. Single input, single output. There are two things that are important for us. The first one is the stability of the system or the response. So one thing that we have to be sure is our system is, our system is stable and our response is going to be stable, and also the performance characteristic of our system. What do I mean by performance? I talk about what's the time constant, what's the rise time, what's the settling time, basically how fast or how slow our system is. Does it have any overshoot, any undershoot, and so on. So all of them are important for us. So these are the concepts that you've seen in your previous course. Time constant is basically what it takes for the output to get up to 63% of the final, up to the time that it takes for the output to get to the 63% of the final value, which is, let's call it final value. And 63% is basically just e to power -1. The rise time is the time for our signal to go from 10% of the final to 90% of the final value. And the settling time is the time that it takes for our signal to basically get within the ±2% of the final value, right? So these are the performance characteristics, some of the performance characteristics of a signal. Right now I'm gonna focus on the stability. So we want to know if our system is stable or not. So one thing that I have to mention and just keep in mind is that there are different definitions for stability. In one definition, we have three kind of signals or three kind of systems. What we call a stable system, or asymptotically stable system. Sorry about that. Asymptotically stable system is for a system that, for a signal that when t goes to infinity, y of t goes to 0. This is called a signal that's asymptotically stable. An unstable system or an unstable signal is a signal that if t goes to infinity, y of t also goes to infinity. That's of course an unstable system, so for unstable signal. So this one is called asymptotically stable, this one is unstable. And marginally stable in this definition is a system that's somewhere in between, that as t goes to infinity, it doesn't go to 0, it doesn't go to infinity, so it either goes to, for example, another, like, settles down at another value other than 0 or infinity, or a system that basically oscillates all the time. Okay, so this is called marginally stable in this definition. There's like another definition that I'm gonna talk about a little bit later, but that's what stability means. Now, we want to see how the stability is related to poles of the transfer function, right? How the poles of the transfer function can give us some information about the stability of the system. So let's just like look at a very simple case where g of s is, or the transfer function is 1 over s plus alpha, right? So the poles of a transfer function is the values of s which make the denominator equal to 0. So for this case, s equal to negative alpha is the pole of the system. Now, if you take inverse Laplace transform of this one, can you guys tell me what the time domain signal is gonna be? Okay, just pause the video and think about it. It's gonna be e to the power negative alpha t, right? So if alpha is bigger than 0, if alpha is bigger than 0, it means that if the pole is somewhere in the left hand side plane, then as t goes to infinity, this also goes to infinity. E to the power alpha t, as t goes to infinity, goes to goes to 0. I'm sorry, right? If alpha is less than 0, let me just do it with another color. If alpha is less than 0, it means that the pole is gonna be in the right hand plane, right? In this case, e to the power negative alpha t as t goes to infinity also goes to infinity. So this is unstable. This is asymptotically stable. Stable. If alpha is equal to 0, then e to the power negative alpha t, it's gonna go to 1. That's like, it doesn't matter what t is, right? It's gotta be equal to 1, right? So this is marginally stable.